Have you ever wondered how mathematicians derive equations for curves and geometric figures? It's a fascinating process that utilizes the fundamental principles of mathematics to create a language that describes the shape and position of these figures. Today, we will delve into this process, step by step, uncovering the mysteries of mathematical equations. Start with a simple line. Imagine a straight line on a graph. The equation of this line is typically written as y equals mx plus c, where m represents the slope of the line and c represents the y-intercept. This equation tells us that for every x value, we can calculate the corresponding y value on the line. Now consider a circle. The equation for a circle with center at the origin of a coordinate system is x squared plus y squared equals r squared, where r is the radius of the circle. This equation is derived from the Pythagorean theorem, which states that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Moving on to a parabola, a curve often represented in quadratic equations. The standard form of a parabola's equation is y equals x squared plus bx plus c. This equation is derived from the principle of completing the square, a technique used to solve quadratic equations. Take the ellipse, a shape that looks like a stretched circle. The equation of an ellipse centered at the origin is x squared divided by a squared plus y squared divided by b squared equals 1. Here a and b are the lengths of the major and minor axes of the ellipse, respectively. This equation is derived from the definition of an ellipse as the set of points where the sum of the distances to two fixed points, called foci, is constant. Lastly, consider a hyperbola, a curve that's the difference of two terms, one of which is squared. The equation of a hyperbola centered at the origin is x squared divided by a squared minus y squared divided by b squared equals 1. This equation is derived from the definition of a hyperbola as the set of points where the difference of the distances to two fixed points, called foci, is constant. To summarize, the process of deriving equations involves understanding the fundamental properties of the geometric figure in question and then translating those properties into mathematical language. For a line, it's about slope and interception. For a circle, the Pythagorean theorem comes into play. For a parabola, the principle of completing the square is used. For an ellipse and a hyperbola, the definitions involving foci guide the derivation. So the next time you see an equation, remember that it's not just a random collection of symbols. Each symbol, each number, each operation has a purpose to describe the shape, position, and properties of a geometric figure. Every equation tells a story of geometry brought to life through the language of mathematics.